Hello everybody. Okay, so second time to do this. So now let's do our study. Yes, section 5.6, that is L'Hopital's rule. So we went over some limit review problems earlier, and now we are ready to study the main one, the L'Hopital's rule. So what is that? First of all, this Frenchman, and his rule can be applied to a limit problem, and x can go to c. The c can be any finite number or infinity as well. And let's say you have one function over another function. It doesn't have to be polynomial. It can be e to the x or natural log of x or sine x. Any function you learned can come in here, okay? When you compute this and you realize that you cannot really determine the limit, and then in that case we call it indeterminate form. And in Calculus 1 class, you learn the 0 over 0 case or infinity over infinity case as an indeterminate form. In this section, we are going to have 5 more indeterminate forms. So altogether, we have 7 different kinds of indeterminate form, and we are going to study. Well, thanks to L'Hopital, we have a wonderful result over here. The thing is, limit. If it turns out that we have an indeterminate form, and then what you can do over here is f prime of x over g prime of x, and the same limit. In other words, we cannot determine the limit, the value of this limit, and then we go over kind of over time. Okay, now we cannot determine it, and then let's see this time if we can determine. So what you do is differentiate the numerator and the denominator separately. Do not use a quotient rule, okay? Then it's going to make it a lot worse than it really is. So we differentiate separately and then take a limit of that. Oftentimes we can finish right here. Well, even after you differentiate it, it is again indeterminate form of like this. And then guess what? We can do it one more time. So one of those examples we are going to see is going to be, you are going to apply the L'Hopital's rule 2 times. So as a result, we differentiate it one more time. Okay? Alright, so and many other different indeterminate forms. Yeah, 5 more. So let's study. Example 1. Is evaluate the limit of e to the 2x minus 1 over x, and as x goes to 0. Okay. How can you do this? Well, plug in, so as x goes to 0, so what's going on here? E to the 0, which is 1. 1 minus 1 is 0, and as x goes to 0. So therefore, this is indeterminate form. It's not flat 0, okay? It's a very, very small quantity, infinitesimally small. So when you have this, I'm going to say this is indeterminate form, so I want you to have a habit of writing what kind of indeterminate form this is. So 0 over 0, well, for that reason, we can use L'Hopital's rule. So I'm going to abbreviate it like LR. Well, what does L'Hopital's rule say? Hello, if this is this, therefore we differentiate it. So I'm going to just first time, minus 1 prime x prime over here. So that is, L'Hopital's rule was applied over here. So at this step, we just differentiate it. So what is that? E to the 2x. So e to the 2x. Well, we have to multiply by 2 because of the chain rule. And then this is 1. So what's going on over here? This is 2 over 1, which is 2. On the other hand, limit of e to the 2x, and as x goes to 0, so this is the same as like e to the 0 times 2. Isn't that right? Therefore, we can say 1 times 2, which is 2. Okay? So, very first thing, you must recognize the indeterminate form. Otherwise, you cannot use L'Hopital's rule. Okay? Sometimes just you overuse L'Hopital's rule. That's the problem. Okay. Example. Next one. Yeah, this board is pretty good, but it leaves a little dark trace over here, so I'm going to erase it 2 times. Oops, a little wet. Okay, example 2. This time, evaluate the limit, which is, oops, that's not good. What can I do? Just 1 second, please. I'm sorry, yeah, but I'm really trying hard to make this one happen, and I try not to use just PDF document for just presenting it. So here we go. Limit x goes to infinity, ln x over x. Wow, this is an interesting case. As x goes to infinity, of course x goes to infinity. What about ln x? Well, do you remember ln x? Of course, ln x graph looks like this. So as x goes to infinity, this one also goes to infinity. So this is an infinity over infinity indeterminate form. Therefore, yes, we can use L'Hopital's rule. So here we go. Limit x goes to infinity. Now, ln x, the first few times I want you to write down each time what you do, okay? So this one is now limit x goes to infinity. The derivative of natural log x is 1 over x. This is 1. So which is what? Limit x goes to infinity, 1 over x. Therefore, what is that? 0. So in summary, okay, let's see what has happened over here. Both numerator and denominator go to infinity. But who is winning? In other words, which one goes to infinity faster? So basically it's like the race to infinity. Well, both are going. So on the other hand, y equals ln x graph looks like this. You see? This one is y equals x, this one is y equals ln x. So this one goes faster. So that means the denominator is dominating numerator. Therefore, the result has to be 0. Okay? So, and the first step is not very obvious, but when you look at the graph, it can be obvious. But once you apply the L'Hopital's rule, it is very clear. Okay? The next one. Example 3. Limit of x squared over e to the negative x as x goes to negative infinity. Okay, x goes to negative infinity. Well, So let's plug in over here. So that means negative infinity squared, which is what? Positive infinity. E to the negative of negative infinity. So e to the negative of negative infinity, also what? Infinity. Okay? So in other words, this is infinity over infinity, indeterminate form. Therefore, we can apply the L'Hopital's rule. So here we go. Are you ready to differentiate it? Okay. X squared, the derivative, and e to the negative x. Take a derivative of that. So now, what is the limit? As x goes to negative infinity, the top one is easy, 2x, over the exponential function, so e to the negative x. And then the chain rule will bring the derivative of the exponent, negative x. So it brings negative sign over here. So what do you see? E to the negative x. Well, again, what is going on? Negative of negative, positive. So this one again, what? Negative infinity over, because x goes negative infinity. And here is negative of infinity. Yeah, negative infinity over here. Therefore, you can apply the L'Hopital's rule one more time. So that makes limit x goes to negative infinity, and the derivative of 2x is 2, and the derivative of this guy. So let's collect all the negative signs over here. We have a negative. The derivative of e to the negative x is e to the negative x times derivative of the exponent, which is negative 1. So eventually this is positive. So this is limit x goes to negative infinity 2 over, this is positive, so e to the negative x. So what is going on here? E to the negative of negative infinity, which is e to the infinity, 2 over e to the infinity. Numerator is fixed to, therefore the result is 0. Okay? So this time, just go beyond that. Okay, we applied L'Hopital's rule 2 times. That is a remarkable thing. On the other hand, when you look at this one is x squared and e to the negative of negative x. So it is kind of e to the x as x goes to, well, as x goes to infinity. You can change it to that. Okay. So this is x squared is increasing over here according to this parabola. On the other hand, e to the x is moving over here like this. So once it goes a little, passes this, it is going to be faster. Okay, e to the x is going to be more exponentially increasing. Well, the picture is not really good, but e to the x is exponentially growing, x squared is just polynomially growing. Okay? Exponential is going to beat any power. In fact, it doesn't have to be x squared. It could be x cubed, x to the fifth. The thing is, when you differentiate the exponential function, this one is going to stay there all the time. In the meantime, when you differentiate the polynomial, each time it loses its power by 1. So in the long run, the power will run out. Okay? Therefore, the denominator is going to dominate. It gives you 0. Oh, by the way, as x goes to negative infinity, you can change it to as x goes to infinity and then changing e to the negative x as e to the x. Okay, that's the same thing. Okay. All right. Okay. one more time. So that you can see everything clearly, all right? Next one is very interesting thing. Example 4, you have an indeterminate form of 0 times infinity. Before we start, let's think about 0 times infinity. It is, again, it's like it will make you puzzle, okay? Well, isn't it 0 if you focus on 0? On the other hand, if you focus on infinity, infinity times anything is going to be infinity. All right? So, it is going to be both are kind of extreme values, extremely small, extremely large, but which one is going to dominate? Again, you are going to see that, okay? And the other thing is, so far, 0 over 0, or infinity over infinity, and to apply L'Hopital's rule, you need a fraction, not a product like this. So, see what happens. Evaluate the limit of e to the negative x times the square root of x as x goes to infinity. Excuse me. The very first, our practical reason. Well, again, 0 times infinity, we do not know the result. Okay? So what are we going to do? Yeah, we want to rely on the L'Hopital's rule, but the L'Hopital's rule requires a fractional form. So how we are going to create a fraction from this product? Have you thought about that? How we are going to change this format so that we can apply L'Hopital's rule? Well, the thing is, e to the negative x isn't it same as 1 over e to the x? Therefore, you can say this is a limit square root of x over e to the x as x goes to infinity. So now it works like a charm over here. So we have a fraction, numerator and the denominator, and as x goes to infinity, square root of infinity is infinity. Yeah, e to the x is infinity. I do not know the details, but I can foretell one thing over here. What is that? E to the x will dominate any kind of power. Okay? E to the x is like an eternal thing, because as you differentiate e to the x, it never changes. It never diminishes over here. So in other words, what I'm saying is the denominator will dominate the numerator, so the result is going to be 0. But that is only just some philosophical idea. So let's use L'Hopital's rule and find out. L'Hopital's rule, limit x goes to infinity. E to the x, the derivative is e to the x. Square root of x, the derivative is 1 over 2 square root of x. Okay, now we can rearrange here so that we can say this one will go down over here. So 1 over 2 square root of x times e to the x. Isn't that true? So now we reevaluate the situation over here. This one will go to infinity and this one will go to also infinity. This time all the infinities are in denominator and the numerator is just 1. It's very helpless kind of situation. Okay? Denominator is absolutely dominating, so the result is 0. So even though we borrowed L'Hopital's rule to conclude the limit is going to be 0, but we can foresee this one, yeah, from the beginning over here. Okay? So you make a mental note. When you have 0 times infinity, you can change this one as 1 over the infinity as like a 1 over, 0 as 1 over infinity. You know what I mean? Roughly speaking, 0 and infinity, they are reciprocals. Alright? So they are reciprocals. So therefore, when you have something times infinity, yes, you can switch this one to 1 over infinity times infinity, which is what? Infinity over infinity, which is the indeterminate form. Okay? So far, how do you like L'Hopital's rule? Isn't it wonderful? It's cute, okay? It's nice. Just do not overuse it, okay? Example 5. Well, this one is going to be our first challenge over here. This time, indeterminate form is 1 to infinity. This is like you are going to say, what about 1 squared, which is 1? What about 1 to the 10th, still 1? 1 to the 100th power, still 1. This is true when you have real, just flat 1. This 1 is very, very close to 1. Okay, in terms of limit problem over here, this 1 is very, very close to 1. So for example, you add just a little bit. In math we use just alpha, okay, or 1 plus epsilon. Yeah, when you add a little bit more and then raise power, and just it goes to infinity. In this case, what's going to happen? It is going to be 1, or it will go to infinity, or it will go to some other number that we already know. Okay? It's going to be an interesting case. So, specific example over here is limit x goes to infinity, 1 plus 1 over x to the x power. So, let's analyze this. 1 is a flat 1, okay? Just exact 1. And here is 1 over infinity, so it is a very, very small quantity. Very, very small quantity. On the other hand, this power goes to infinity. This is I was talking about earlier, like 1 plus epsilon to the infinity stuff. So this one it will be just 1. This is ignorable, so it's going to be like 1 or something else. So we are going to find out. Okay? Oh, by the way, this Greek letter, lowercase, is epsilon. Well, earlier when you did some in the limit review, I asked you a question like y equals x to the x. How do you differentiate it? Does anybody remember how to differentiate this? Well, in order to differentiate this, we took a log on both sides so that once we apply the properties of log over here, it becomes x times ln x. We separate this exponent from this main body so that it becomes x times